I probably should have told you this earlier, but when I started teaching you guys logs, you guys did really well with it, as far as like doing them in your head. But maybe some of y'all are like faking it. So if you're that person that's having trouble with doing logs in your head, that does sound hard, doesn't it? I just have like a little thing I want to show you. So, do you want to see my, you know how I have like little weird things in it, right? So anyway, let's make it 10. You see my 10? It's a 1 and a 0. It's a 10 to the negative 5. See it? Do you see it?
Yeah.
If I take the log of this, then I'm going to chop the tree down, and then the 5 falls to the ground. And so the log of 10 to the negative 5 is negative 5. Okay.
Is it really?
No, it really is. I made that up, but I didn't tell you guys because y'all weren't having trouble. I told Mr. Willingham about it, and he made fun of me, like, openly. And he was like, you shouldn't tell people that because that's why they think alligators eat the bigger numbers. And I don't know about y'all, but I'm still pulling the alligator out when I'm looking at inequalities. Are y'all still thinking alligator? Because what's wrong with it? So if you have to take a log of something, then just chop the tree down, and then the number will fall to the ground. You're welcome. The other thing, Henderson-Hasselbalch, okay? So when you do Henderson-Hasselbalch, it's pH is equal to pKa plus the log of, and A is on top, and the acid is on the bottom. If you have to use Henderson-Hasselbalch with bases, it's the same thing, but it's POH is equal to pKb plus the log, and then this part's flipped upside down. It's just, it is what it is. So if you ever have to do that, that is it. I haven't, I did those things that y'all did for homework. I did that like 2 or 3 weeks ago before I actually taught you this, and I didn't know if it would, like it didn't click to me that wasn't in the PowerPoint. But I haven't seen the Henderson-Hasselbalch version of the basis in a lot of the College Board stuff, but if it ever comes up, it's the same thing. You just have to flip the acid and conjugate base upside down right here. But everything else is the same, and obviously you want to use pKb since you're doing base stuff. The other thing is, this is a ratio right here. That's a ratio. So you can do molarity over molarity, or you can do moles over moles. That's going to give you the same thing. Because if you have 500 milliliters of solution and 2 moles of one and 1 of the other, when you take 2 and divide it by 500 and 1 divided by 500 and you take a fraction of that, like you're going to get the same, it's going to be the same ratio. So it doesn't matter if you do moles or molarity. And that's all. That's all the things. I mean, just like little tricks along the way, right? Anybody got any questions about that? Okay. So going back to this, when you titrate, it doesn't matter as far as molarity. When you do strong or weak acids or bases, if you have the moles of hydrogen equals moles of hydroxide, like it doesn't matter. Like on your quiz, you had to titrate weak acid, and it didn't matter, right? You still calculate that the same way. Hopefully, you didn't have any trouble with that, right? Is that okay? Y'all give me sad looks. Are you all right? I'll grade your quizzes later. Was it all right? No?
No.
No?
I didn't know if
You didn't know how to, was it both of you didn't know how to do, or?
I don't know if I mixed up.
Don't know if you mixed it up. Okay. I might work out one of your quiz problems for you if you want to see that. I'll do that for you. I don't care. Just don't tell your friends, okay? Let's go ahead and look at this, though. I just want to show you something. This half equivalence point, that comes up a lot. So if I draw a titration curve, that looks good. I'm such a good artist. This is the equivalence point, and then like if this is 20 milliliters or whatever, then 10 milliliters, this guy, that's a half equivalence point. And that's where, you know, your pKa equals pH. That's where your acid is equal to the molarity and all that stuff. Like that, not molar. This guy, right? This is equal to that. That's what I'm trying to say. The molarity of the conjugate acid is, base. This is that. Okay. So that's the half equivalence point. And so that's a little tricky thing that you might see. And I just wanted to I'm going to do this one with you real quick. So let's look at this. Determine the volume of 0.5 molar NaOH that must be delivered to reach the half equivalence point. And so the pH at the half equivalence point is measured to be 4.74. Find the pKa. Before we even go on, if the pH at the half equivalence point is 4.74, then what's the pKa? Okay, good. So let's look at and then identify the main species that are present. So let's look at this. The moles, you know how to do that. So if this is the moles in the solution initially, if we're trying to only reach the half equivalence point, just use your head, okay? This is a 15. We're only trying to reach half equivalence point. How many moles of sodium hydroxide do I need? 7.5. Okay, so if you see half equivalence point, just know you're only going to get about halfway there. And so if we do that, then the reason this is 0.75 moles is because that's half of that. And there's your molarity flipped upside down basically, and then you just need 0.015 liters. Do y'all have this like written in your notes? Is it already written down?
Yeah.
Might want to write it down. Some of your practice problems have half equivalence things. Yes, sir? Sure. Okay, so it's half equivalence point, and so the half equivalence point is that flat place where pH equals pKa on the titration curve. And so at equivalence, if I need to have, if I have 0.15 moles of acetic acid in the solution, then to make it equivalent, I need 0.015 moles of sodium hydroxide to get to the nice actual equivalence place. But if I only want to make it halfway to the equivalence point, then I only need half as many moles. And so if you take 0.015 divided by 2, then you get 0.0075. Right, and so if I only want to neutralize 0.0075 moles of acetic acid, then I only need 0.0075 moles of sodium hydroxide. Is that sitting okay? Yeah. Okay, cool. So, like I said, at the half equivalence point, that's where pKa and pH are equal. So the pKa and the pH are both going to be 4.74 because the log of 1 is 0. This is this old stuff right here. And then the main species present at the half equivalence point, I like to draw this little graph. I'm just going to cut up through there. At the beginning, when I don't have anything else in there, I have the acid here, right? And then at equivalence, I don't even think they have water. Oh, no, they didn't have this guy. The sodium is coming from the hydroxide, right? So at the beginning, I have that, and some of that's going to dissociate, right? So at the very beginning, I have that. Are we okay there? You all right with the idea of that? If I don't need to write down the whole equation, if I add this to water, then I get that guy. You okay with that? And so once I start titrating that, I'm gonna have a little bit. Well, actually, I should have just wrote out the equation. Can I do that? That's always the answer. I hope you learn from my mistakes as I talk in front of you. Like, I always write everything down, and then I don't, and then I screw up. So anyway, there we go. So that's gonna, at the beginning, that's what you have. So you do have a little bit of the acetate. So this is before I even begin, just in the water. So if I add enough sodium hydroxide to get to the half equivalence point, would I not have some sodium floating around in there too? Yeah, so sure. And so that's what I have, those four things. Any hydroxide that from the sodium, sodium hydroxide, any hydroxide is actually going to be combining with this to make water. So I'm not going to have any hydroxide in the solution because every drop of hydroxide is going to get neutralized because I have enough acid present. So you're not going to basically have everything at the half equivalence point except hydroxide. And water's not up there because we don't really take it into account, but water's in there obviously. You okay? All right, so just show you a couple more things just with some pictures that you probably already are familiar with. So, like I had already told you guys, if you look at a titration curve for a weak acid and a strong base, or a weak base and a strong acid, if you have a base, you know, and you're titrating a base, it looks just like this, except it goes like that, right? And you're going to do some practice with that today, so don't let that freak you out. But bases are going to start high and at equivalence, they'll meet and then go that way. But when you're titrating a weak acid, you'll see that this is kind of squished down, and this is has a little bit more of an angle to it. If you have a strong acid base, it'll be sort of a taller curve, and this will be flat here and flatter there. And you'll see that a little bit when I show you the next picture. I don't know if I already showed you the strong acid and base picture. I think I might have already. Did I already? Okay. Well, the only other thing that I need to show you then is polyprotic acids. And so what they'll say with this, like let's just say that I have phosphoric acid. This is scary. Stop looking at it. Is that terrifying?
Yep.
Okay, so stop looking. I'll make it okay. It's going to be fine. Let's say I have something like H3PO4. Do you know how I told you that acids are going to lose one hydrogen at a time? Okay, so this is a polyprotic acid. Poly meaning many, and protic is talking about the proton. And the proton is what element? Yeah, so good. And so it has 3 label or mobile or whatever protons. I think they'll say label. I don't know how to say it, but that's how to spell it. I think I was right the first time. But anyway, so if I take phosphoric acid, and let me just kind of show you that. See if I can draw this without screwing it up. So it's phosphoric acid is a weak acid. So my pH is going to start around not 1, but maybe around 2 or 3 or something. Now, this is all estimating. I mean, I would need the pKa's and all that. And I'm just going to eyeball it for you. I feel like that's going to be better. So anyway, if I add sodium hydroxide, what's going to end up happening is I'm going to have this buffering region where H3PO4. I still have H3PO4 and I'm buffering. And then I'm going to have a little equivalence point. And now I'm going to have H2PO4 minus. That's still an acid, it's still a weak acid. And I'm adding sodium hydroxide, and then I'm going to reach an equivalence point where that is equal to the hydroxide. And then I'm up here, and I'm at HPO4 2 minus. And so basically, you can look at how many little flat parts to the curve you have, and you can sort of tell how many hydrogens were in the acid. Yes, sir?
So that graph on it will flatten back out.
Yes.
I mean, I wasn't trying to
No, you're fine. And so since it does flatten back out, I guess it would be better to look at how many humps it has. I mean, this isn't in a book, like count the humps or count the lines. But if that, you would have an extra flat part. So tell you what, count the humps. Does that, yeah, that works. 2,
phosphate.
Yes. Yes. Right. And so your phosphate would be your like conjugate base or the hydrogen phosphate.
Right.
And so just basically one hydrogen is lost at a time. You don't have to do any math for this. So yeah. So if we have this little guy right here, notice that these are going to have pKa values, and it'll have one, so the first hydrogen loss will have its own pKa value, and the second hydrogen loss will have its own pKa value. And so if we count the humps, we have 1, 2, and so that works out. Don't count the flat planes, count the humps. But so we had, this is a diprotic acid then, so it has 2 protons. Also, if you have like a base that has 2 hydroxides, then it's like dibasic. Tribasic, isn't that interesting? Well, tribasic wouldn't be a thing, but I guess it could be. And so you might have to look, you don't have to do any math for this, I know that's a thing. But you need to know that the pKa value, or the Ka value, let's talk about that for a second. As Ka goes up, pKa goes down. Do you remember that? Okay, so if you look at the pKa, this is lower than the second one. So basically when you have this polyprotic acid, the first acid is going to be the strongest one. And then the second acid is weaker, and then the third is weaker than that. So if we look at pKa values, lower, and then we'll get a little bit more and a little bit more. As the pKa gets higher, the acid is weaker. So there's that. And we have some practice with that today. Acid-base indicators, they basically are equilibrium and they shift. And then I already told you this, but when these concentrations are equal, then pH is going to equal pKa. And on these, they're just going to give you a list of indicators. And on my test I took the test last night, and it was fine. We're doing like worst case scenario stuff, and it's not that bad. But you want the indicator that has a pKa closest to the pH of the equivalence point, and that's right here. That's very important. I did go ahead last night and make okay, let's do this one real quick. Make the study guide, and I put it on Blackboard. So here's a bunch of indicators. Which one would I want to use when I have a strong acid and a strong base? This looks just like something on the test. This is a test question. Which one would you want to do? Bromthiamyl blue, that's right. Yay, good job. Now let's talk about this for a second. Bromthiamyl blue is the answer. Yes, good job. But like, even if I had to use phenolphthalein, isn't it around 9 that it's 9 point something? So if you have to use phenolphthalein, a lot of times I've used phenolphthalein. We used phenolphthalein last week, and we had we were doing the vinegar with that? Yeah. So our pKa value, let me say this better. Our pH at equivalence was 8 point something. So that was a good match. That was a better match. But even if you had to use it for this, you would still be within that like 1 drop area. So it wouldn't really be the end of the world, but bromthiamyl blue would be better. So what would the indicator be good for acetic acid and sodium hydroxide? Phenolphthalein. Okay, so, and then you can see that's a better fit. Yay! And that's all there is to this. Now, we're going to do some practice. I think I should go over, I looked over y'all's little quiz results from Friday. And let's go over a couple of these. So, just a few of them. 12 and 14 were particularly bad. So, let's start with 8, though. I have 8, 10, 12, 13, 14, 15. And I don't know if 13, 14, 15 were bad because they were hard or because you were in a hurry. Okay, so let's start with number 8, though, okay? So, number 8 had, you were asked to make a buffer with a pH of 9, and you had 1 molar hydrocyanic acid and sodium cyanide. Yeah, cyanide. I don't know what I'm thinking. Anyway, so which of the following statements? So if you look at the pKa, I think I might need to write this one down. Did anybody struggle with this one? Okay. Do you mind? Let me just write this one down for you. Look on with Jacob if you need to. This is very much like something that you're going to see on my test and the AP exam. that whole giant long process of making a buffer, that's good and that might come up, but this is more like what you're gonna see. So if I look at this Henderson Hasselbalch, right? I want my pH, right? My pH needs to be around 9. Can I do this pKa in my head perfectly? No. Can I chop down that tree and tell it's around -10? Can I tell it's bigger than 9? Yeah. Pick a number bigger than 9. It doesn't matter if you pick 47 million or 9.2, but pick a number. I mean, obviously it wouldn't be bigger than 10 either, but pick a number. You need to take a second to write stuff down and look at it and think about it. So, if my pH needs to be 9 and my pKa is 9.2, do I need more acid or base? Yeah, and that's how to do that one. Do you see how that's not magic? Okay. Number 10. On number 10, strong acids. Oh, just kidding. Looked at the wrong side. Number 10, a certain buffer has a pH of 4.6. The weak acid used to make this solution. HA has a pKa of 3.2. And so this is the same thing. 4.6. And then, I don't have a paper in front of me. 4.6 and 3.2 of that. So, which one is in heavier concentration, the base or the acid? The base. Because you have an acid, well, acidic, right? And I needed to be higher, so I need more base. Does that answer that one question for you guys? That correlate to what you had to do? Yeah.
Last night I did it. I didn't write down.
Well, this is the kind of thing you're gonna see a lot. Like yeah. I actually edited your test last night because I had a dumb question I didn't like. I was like, everybody's gonna miss that one. It's not worth. That's not the hill I would die on. Like, that's a dumb question. So I took and I made like a buffer question like this, another one, because it's good stuff. Sorry. So if you don't like that, better like it to get to liking it. 12. 12. I think I almost missed 12 when I did this one, but I went back and it just is because it's like out of alphabetical order. Or do you not understand it? Like.
The thing I did was I chose acid.
Yeah, and so if you look at it, as far as which one has a greater pH, the pH is going to be, see, this is where I'm going to, so it needs to be more basic. So you need the weaker acid, and so that ends up giving you that second one, right? HA. And it's like, there's a lot of questions on the test where you have to think about pH, pKa, and then the pH like 7 or above and less, and it's hard. These are hard because you kind of think, okay, stronger acid, but then that makes the pH lower if it's stronger acid, and so it's a little bit backwards. So 12 had a lot of y'all miss it. 14 was bad. So, 14 is actually super easy though. Is that a weak acid?
No.
Yeah. So, what is its base going to be? Relatively strong. And so, when you titrate a weak acid, its pH has to be basic. And when you titrate a weak base, its equivalence point will be acidic. And so, the only number above 7 was 8.72. There's no way for you to mathematically do that without a calculator and like some time on your hands. But you do, so not hard question, but tricky. So 15, we're titrating. And so this one is why if you had trouble with the quiz, this is the thing. So when we go into this, let's say I have 2 beakers. Equal volume, equal molarity. And I got some hydrogens. I have 4 hydrogens in here. And I actually have racked my brain for like a cute story to use to explain this, and I haven't come up with one yet. I'm gonna have to take a couple more showers or drive more, or like some crazy stuff comes to me. But anyway, you have the same molarity. Let's see if we have the same molarity of calcium hydroxide and sodium hydroxide, right? So let's just put 1 drop of sodium hydroxide in here. I don't know, this isn't like really a drop. Okay, there you go. And let's put a drop of calcium hydroxide in here. You see where this is going? Let's put 1 more drop of sodium hydroxide in here. And let's put 1 more drop of calcium hydroxide in here. Do you see with every little particle of calcium hydroxide, I get 2 hydroxides? So how many? I'm neutral over here now. Do you see that? 2 drops. So, 2 molecules, whatever. Oh, I should have circled that differently. But it only took 2 moles, if you will, or 2 whatever. No, can I act like I didn't do that? Oh, that was ugly. There. All better. It took 2 drops over here, and then with 2 drops, I'm not there yet. I'm only halfway there. So I would need 4 moles, or twice as much of the same molarity, because you only get 2. You only get 1 hydroxide off the sodium one. So I don't know of a better way to explain it to you other than that. I don't have a cute story. So as far as the math goes on that, I guess my key to the quiz is somewhere right here. What was the, and I have people watching this. I haven't taken this, so I'm turning it off. Bye, people. I'm done talking, by the way. We can use the rest of class. I mean,